Welcome to this deep dive, everybody. It's a big one. Geology, climatology, and economic geography. All from PowerPoints, PDFs, and even a couple of audio lectures. Whew.
Sounds intense. Well, you're in the right place. We'll break it all down, get to the key stuff so you can ace that exam.
And I have a feeling that these subjects, they're probably more connected than people realize.
Oh, absolutely. Understanding geology can give you a real advantage in climatology. And then those two, they really tie into economic geography. It's about that big picture.
Yeah, exactly. So let's start building that picture. Foundation first, geology. So one of the first things that jumped out looking at this material was Earth's structure. Kind of like a giant layer cake.
Great analogy.
Yeah.
So we've got the crust, the thinnest layer, like the icing on that cake. Under that, the mantle, much thicker, acts like a really, really viscous fluid over millions of years. And then at the heart of it all, we've got the core. Super hot, mostly iron and nickel.
Wow, and how do scientists even know what's going on way down there? We can't exactly dig that far, right?
Right. That's where seismic waves come in. You know, the waves from earthquakes. They travel through the Earth, but at different speeds. It all depends on what kind of material they hit. So by analyzing those waves, we get a map of Earth's internal structure, kind of like an ultrasound.
An ultrasound for the whole planet. That's amazing. And this understanding of Earth's structure, that's what leads us to plate tectonics, right?
Exactly. The Earth's crust, it's not one solid piece, you see. It's broken up into these massive plates that are always moving, crashing, rubbing against each other. All that movement, that's what creates mountains, valleys, even volcanoes and earthquakes.
Wow, so the ground we're standing on is always on the move.
In a way, yeah.
I remember from the lecture something about convection currents in the mantle being what makes those plates move.
Picture a huge pot of soup, simmering, real slow motion.
Yeah.
The heat from Earth's core makes these circular currents in the mantle, and they kind of drag the plates along with them.
So the Earth's own internal engine is shaping the surface. That's incredible.
And it's been going on for billions of years, shaping and reshaping. The Himalayas, for example, they're actually still growing because the Indian plate's colliding with the Eurasian plate.
Mind-blowing. And speaking of dynamic, let's talk about volcanoes and earthquakes. This material gets really detailed about the different types of waves, the seismic waves that earthquakes make.
Oh yeah, super important to understand those. First up, primary waves, or P waves. They're compressional, like sound waves, and they travel the fastest. When an earthquake hits, they're the first to arrive at a seismograph.
So they're like that initial shock. And then we've got secondary waves.
Right, secondary waves, or S waves. They're transverse waves, so they move up and down and a bit slower than the P waves. But here's the key thing about S waves. They only go through solids.
Okay, and why does that matter?
Well, it tells us that Earth's outer core is liquid. Those S waves can't get through it, so they create what's called a shadow zone on the opposite side of the Earth from where the earthquake happened.
Like a detective using clues. And what about those Rayleigh waves and love waves? I saw those in the PowerPoint.
Those are the surface waves, the ones that do the most damage. They've got these really complex vibration patterns. They travel along the Earth's surface, and that's what causes all the shaking we feel. Buildings topple, infrastructure gets messed up.
PowerPoint had all these numbers, the speeds those waves travel through different stuff. Gravel, sandstone, granite.
That's vital info, for earthquake preparedness and for building structures that can handle it. Denser rocks like granite, they transmit those waves way faster than loose stuff.
It's like a whole hidden world of waves going on under our feet.
You got it. And shifting gears a bit to volcanoes, remember, different types, each one linked to specific plate tectonic settings.
Right, the PowerPoint had effusive and explosive volcanism. What's the difference?
Effusive is like relatively chill eruptions, flowing fluid lava that usually happens at spreading zones where the plates are pulling apart or at hot spots, like the Bardarbunga eruption in Iceland back in 2014.
So more like flowing lava, not big explosions.
Exactly. Explosive volcanism, that's a different story. Happens where the plates collide, one gets forced under the other's subduction, the sinking plate melts, makes gas-rich magma, and that erupts with incredible force.
That sounds terrifying.
It definitely can be. Explosive eruptions, they create those pyroclastic flows, superheated clouds of ash and gas, rushing down mountainsides insanely fast, and lahars, which are volcanic mud flows. Remember the 1985 eruption of Nevado del Ruiz in Colombia? Over 20,000 people died.
It's a sobering thought. The PowerPoint also mentioned volcanic rocks. Pumice.
Oh yeah, pumice.
Yeah.
Forms from that gas-rich lava, cools so fast the gas bubbles get trapped inside, makes it super light, can even float.
It's amazing how something so light can come from such a powerful event. What about those other volcanic things, fumaroles, hot springs, geysers?
All about the heat and gases released from the magma below. Geysers are pretty cool, periodically erupting with steam and superheated water. Think Iceland and Yellowstone.
Bucket list for sure. But the material also brought up that Nile-Sea disaster in Cameroon.
Right, a really tragic reminder of the hidden dangers. Back in '86, Lake Nyos had this limnic eruption, released a huge cloud of carbon dioxide. It flowed into nearby villages, and a lot of people died. Shows just how important it is to understand and monitor these volcanic hazards.
A reminder that nature, it can be both amazing and dangerous at the same time. Okay, so from the internal forces to the external ones, weathering and erosion.
Good transition. These processes are constantly shaping the world around us.
One of the PowerPoints said weathering is the breakdown of rocks, both mechanically and chemically.
Think of physical weathering like smashing a rock with a hammer. Smaller pieces, but the rock itself doesn't change. Chemical weathering, that actually alters the rock's chemical makeup through reactions with water, air, acids. Carbonic acid weathering is a big one.
So physical, it breaks down, but chemical weathering transforms it. What's the connection between chemical weathering and the carbon cycle?
Well, the carbon cycle, is how carbon moves between the air, oceans, land, living things. Carbonic acid weathering, it pulls CO2 out of the atmosphere. Rainwater absorbs CO2, becomes a weak acid. That acid dissolves certain rocks like limestone.
So the carbon gets locked away in the rock.
Yep. And the PowerPoint used the Great Barrier Reef as a great example.
That massive reef built by those tiny coral polyps over millions of years.
And it formed largely through carbonic acid weathering. Those polyps, they build their skeletons from calcium carbonate, and that pulls dissolved carbon out of the seawater.
So the reef is like this huge carbon storage facility. The PowerPoint also talked about the Swiss Alps, the Jura Mountains, even the Devil's Marbles in Australia, all shaped by weathering.
Perfect examples. Shows how these processes, over vast amounts of time, can create some truly amazing landscapes. Weathering sets the stage, and then erosion comes in, carries the weathered material away.
So erosion is all about transport. Water, wind, ice, gravity, like rivers carving canyons.
Right on. And remember those stunning alpine lakes from the PowerPoint. Lake Garda, Lake Maggiore, formed by glacial erosion during the last ice age.
I can't even imagine the power of glaciers carving out those huge basins. And glaciers also move rocks around, right? Leaving those foundlings, the erratic blocks.
Yeah, those erratic blocks are like clues left by the glaciers, telling us their size and where they moved. And speaking of ice, can't forget permafrost, the ground that stays frozen, up in the high mountains and polar regions.
The PowerPoint said permafrost covers something like 5% of Switzerland. Why is that a big deal?
Well, permafrost has a crucial role in those environments, but as temperatures warm up, it thaws, and that causes problems.
Okay, no problems.
Thawing permafrost can destabilize slopes, so you get more landslides, rock falls, and it releases methane and CO2, greenhouse gases, into the atmosphere.
So it's a double whammy, more hazards and contributing to climate change.
Exactly. It really shows how climate change can trigger this chain reaction across the planet's systems.
Well, that wraps up our geology deep dive. Pretty incredible how dynamic Earth is with all these forces shaping and reshaping its surface.
Definite dynamic, and it gets even more apparent when we move on to climatology, studying Earth's atmosphere and what drives weather and climate.
Perfect. Onto the atmosphere, the next layer of our Earth exploration.
Ready for the atmosphere? Fascinating system keeps our planet's climate in check.
Absolutely. One of the first things I noticed in the material was how the atmosphere is structured, in layers.
Like another layer cake, each one with its own quirks. The troposphere, that's the one closest to Earth, goes up about 10 kilometers. That's where all the weather happens, clouds, rain, wind, storms, all that.
So that's where the action is. What about above that?
That's the stratosphere, stretches up to around 50 kilometers, way more stable than the troposphere. And importantly, that's where the ozone layer hangs out, protecting us from all that nasty UV radiation from the sun.
Ozone layer. Earth's sunscreen. Got it. Okay, so the lectures also talk about air pressure. What is that exactly, and why is it so important?
Air pressure. It's just the weight of the atmosphere pressing down on the Earth. The higher you go, the less air pressure there is. Like a column of air gets thinner and lighter the further you are from Earth.
The slideshow had this cool visual showing how air density and pressure, they both go down with altitude.
Exactly. And this explains, why your ears pop on a plane. As the plane goes up, air pressure outside drops, and the air trapped in your ear expands, pushes on your eardrum.
That's why chewing gum or yawning helps. Right. It equalizes the pressure.
You got it. And air pressure also explains why a candle flame goes upwards. Heat makes the air molecules move faster, spread out, they become less dense. That warmer air rises, and you get that upward draft.
So warm air rises, cooler air sinks. Seems like such a basic idea, but it drives so much of what we see in weather.
Absolutely fundamental. Works on a local scale and a global scale. Think about those sea breezes you get at the beach.
Oh yeah, they always seem to kick in when it's hottest.
Because the land heats up faster than the water, creates this low pressure area over the land. That pulls in cooler, denser air from the sea, boom, onshore breeze. At night, reverses, and you get an offshore breeze.
All comes back to that warm air rising, cool air sinking.
Yeah.
And this same principle, it drives global wind patterns, right?
Precisely. And one of the key players in all of this is the Intertropical Convergence Zone, the ITCZ.
Right. The lecture mentioned that. It's this band of low pressure circles the Earth near the equator.
That's where the trade winds from the northern and southern hemispheres meet. All that warm, moist air goes up, cools, condenses, and you get rain. That's why the tropics are so rainy.
The ITCZ is like this giant rain-making machine.
Pretty much. And as this air rises, spreads toward the poles, it cools down, eventually descends, and creates high-pressure areas around 30 degrees latitude, both north and south. That descending air is super dry. That's why a lot of deserts are at those latitudes.
So the ITCZ, it affects rainfall and even desert formation. It's amazing how it's all connected. The material also mentioned the Coriolis effect, something to do with Earth's rotation, I think.
Imagine you chuck a ball straight north from the equator. While it's traveling, the Earth's rotating underneath it. So to someone standing on the ground, the ball looks like it's curving to the right, eastward in the northern hemisphere. In the southern hemisphere, it curves left, westward.
So the Coriolis effect makes things traveling long distances appear to curve. How's that connected to wind?
Wind's just air moving, right. Because of the Coriolis effect, winds in the northern hemisphere, they get deflected to the right, and in the southern hemisphere, to the left. That's why those global wind patterns, they don't just go straight north or south, they curve, create those big circulation patterns.
That makes sense. So while global wind patterns are affected by those big forces, local wind patterns are often shaped by topography and temperature differences, right? One of the lectures used the foehn wind as an example.
The foehn wind's a cool one. It's this warm, dry wind, happens when moist air is forced to rise over mountains.
The lecture used the south wind hitting the Alps. What happens there?
So that moist air, it's going up the Alps, it cools down, water vapor condenses, you get clouds, precipitation. Once it's over the top, it goes down the other side. As it descends, it gets compressed, warms up about 1 degree Celsius every 100 meters.
Okay, so it's compressed, warmed up. But what about the dryness? Why is the foehn wind known for being so dry?
Well, it dumped most of its moisture on the other side as rain or snow. So the air coming down the leeward side, it's much drier, and you get those warm, dry, foehn conditions.
The one side of the mountain, cool and damp. The other side, blast of warm, dry air. A totally different microclimate.
Exactly. And that can have a huge effect on local weather, snowmelt, plants, even how people live and work there.
It's amazing how such different conditions can exist so close together. Well, that brings us to something we can't really avoid these days. Climate change.
A big one and complex, but we've got to understand it if we want to do something about it.
One of the things that tripped me up at first was the term greenhouse effect. The slideshow called it a natural process, essential for life. But I thought the greenhouse effect was bad.
Got to separate the natural greenhouse effect from the enhanced greenhouse effect. The natural one, that's what makes our planet livable.
Okay, so how does that work?
Think of the atmosphere like a giant greenhouse. The sun's energy hits Earth as shortwave radiation warms the surface. Then, Earth radiates some of that energy back out as longwave radiation. Certain gases in the atmosphere, CO2, water vapor, methane, they trap some of that outgoing radiation, and that keeps Earth warm enough for life.
So those greenhouse gases are like a blanket trapping heat.
Exactly. Without that natural greenhouse effect, Earth's average temperature would be like -18 18 Celsius. Way too cold for most things to survive.
So the problem isn't the greenhouse effect itself, it's that we're making it stronger.
You got it. Burning fossil fuels, it releases tons of greenhouse gases, basically thickens that atmospheric blanket, traps more heat, like we're cranking up the thermostat.
And that's where the disruption of the carbon cycle comes in, right? One of the sources used this analogy, adding more water to a bathtub than the drain can handle.
Perfect analogy. We're putting carbon into the atmosphere faster than natural processes can take it out. That extra carbon's what's driving this enhanced greenhouse effect and causing climate change.
And then there are those feedback loops that can either amplify or dampen the warming, right?
Positive feedback loops, they make things worse. Classic example. Melting ice. Glaciers, ice sheets melt. They expose darker surfaces underneath. Those absorb more heat, and that leads to even more melting.
Like a runaway train. What about negative feedback loops?
Those could potentially help counteract the warming. Like as temperatures go up, more water evaporates, maybe more clouds form. Clouds can reflect sunlight back into space, help cool the planet.
So it's a battle between these positive and negative loops. It all sounds kind of scary, honestly. Is there any hope? What do the sources say about solutions and challenges?
It's a huge challenge, no doubt, but not hopeless. We have the knowledge and technology to switch to a more sustainable way of life, but it takes everyone working together.
So where do we even start?
The sources had a few ideas. Individually, we can lower our carbon footprint, like taking public transport, using energy-efficient stuff, eating less meat.
Those are all good. But it sounds like we need bigger changes too.
Absolutely. We need a complete change in our energy systems, ditch the fossil fuels, go for renewables. That means government policies that make those changes happen and hold polluters accountable.
One of the slideshows had this phrase, the polluter pays principle. What did that mean?
Basically, those who've done the most damage, they should bear the costs of fixing it. That's the idea behind things like carbon taxes and emissions trading schemes.
So making sure the costs fall on those who created the problem. Seems fair, but I bet there's pushback against that.
Oh, there's definitely political challenges to putting those policies into action. But if we delay, the impacts will just get worse and it'll cost more to fix things later.
It's a reminder that climate change isn't just an environmental thing, it's economic, social, political.
Exactly. And don't forget, your voice matters. Speak up, raise awareness, fight for change.
I like that, using our voices to push for a better future. Speaking of sustainability, that leads us nicely into economic geography, how economic activity is spread out, and how it relates to the environment.
It's a field that helps us understand the spatial dynamics of economic development and how it affects the planet.
One of the PDFs I was reading started with explaining the difference between renewable and non-renewable resources.
Renewables can be replenished naturally, fairly quickly, while non-renewables are finite, take millions of years to form.
So things like solar energy, wind power, sustainable forestry, those would be renewable. Non-renewable would be fossil fuels, coal, oil, natural gas.
Exactly. And our dependence on those non-renewables is a big reason we're in this climate mess. That PDF had this really stark example of unsustainable resource use, the Aral Sea disaster.
What happened there?
The Aral Sea used to be the fourth biggest lake in the world. But then, in the mid-20th century, it started shrinking like crazy. They were diverting water for irrigation, mostly for cotton and rice in the Soviet Union.
So they basically drained a lake to grow crops.
Pretty much. And the consequences were awful. The lake shrank, it got way saltier, killed off the fish, destroyed the fishing industry. The exposed lake bed, it turned into this source of toxic dust storms, messed up people's health, ruined crops. The whole ecosystem collapsed, and the economy tanked.
A real lesson in what not to do. The PDF said they've been trying to stabilize the northern part, but it's still really bad.
A cautionary tale, right. Shows how important sustainable resource management is and what happens when you prioritize quick profits over long-term environmental health. Now, for a more positive example, let's look at Switzerland's transportation policy, particularly the NEAT project, the new rail link through the Alps.
I've heard that. Those amazing tunnels through the Alps, incredible engineering.
The Gotthard Base Tunnel and the Lutschberg Base Tunnel, they're designed to shift freight transport from trucks to trains, make it more efficient and eco-friendly.
So instead of all those trucks clogging up the mountain passes spewing exhaust, the cargo just zips through on trains. But what about the cost of building something that big?
That's where the sustainability triangle comes in. The NEAT project wasn't just about the environment, it was also about making Switzerland's economy more competitive. Faster, more efficient transport means a stronger economy.
And it must have created a ton of jobs in the rail sector, right?
For sure. Though there were some worries about job losses in the trucking industry, but overall the economic benefits were huge. And don't forget the social side of things. Cleaner air, so people are healthier, safer transport, and even stronger cultural links within Switzerland, better connections north to south.
It's a great example of how these big projects can achieve a lot of different goals. But I imagine something on that scale must have had some challenges too.
Oh, tons. Those tunnels were crazy expensive, needed some creative financing, and there were worries about environmental impacts during construction. It's a sensitive mountain environment. Making sure the benefits were spread fairly, that was a big consideration too.
Shows how complex these large-scale projects are. So many things to consider, so many potential trade-offs. Which brings us to our last topic, spatial planning in Switzerland.
Spatial planning, it's about making smart choices about how we use land for everyone's benefit, finding the right balance between development and protecting nature, especially in a country as densely populated as Switzerland.
The material mentioned this idea of economical use of land.
It means getting the most out of the land we have without sprawling everywhere and trashing the environment. Think high-density housing, mixed-use development, and preserving green spaces.
Makes sense. The material also said spatial planning happens at different levels in Switzerland: federal, cantonal, and communal.
Got to make sure decisions are made at the right level, taking into account local needs and priorities. The federal government, they set the big framework. The cantons develop plans for their areas. And the communes, they handle the nitty-gritty zoning, building permits, all that.
So it's like this layered system. Each level builds on the one below it.
You got it. And to show how this works in practice, the material looked at the challenges of developing wind energy in Switzerland.
Wind energy. I can already see where the conflicts might come in.
Exactly. Wind energy, it's clean, renewable, but finding good spots for those giant turbines in a country known for its beautiful scenery and charming villages, that's tricky.
The classic NIMBY problem.
You said it. The material highlighted some cases in cantons like Appenzell and Glarus, where they wanted to put up wind turbines, but people locally fought it hard. They were worried about how it would look, the noise, the effects on tourism and property values. Those concerns often outweighed the need for clean energy.
Shows the challenge of balancing national energy needs with what people want in their own backyards.
Mhm.
And it's not just about finding the right spots, it's also about managing how variable renewable energy is, right?
Another layer of complexity. The material pointed out that hydropower, a major source for Switzerland, it fluctuates with the seasons, peaks in spring and summer when the snow melts. Wind and solar have their ups and downs too. So creating a reliable and sustainable energy system, that's a puzzle.
Sounds like a big one.
And to illustrate the trade-offs and complexities, the material looked at the Trift project.
The Trift project, what's that?
Imagine damming a shrinking glacier in the Bernese Alps to make a reservoir for hydropower. That's Trift in a nutshell.
Ambitious, but I bet it's controversial.
Oh, it's caused a ton of debate. People who want more renewable energy, they're up against those who are worried about the environmental impact on this pristine mountain landscape.
So who's right?
That's the million-dollar question, and there's no easy answer. People who support it say it's crucial for getting Switzerland off fossil fuels, meeting its climate goals. They say the project's designed to minimize environmental harm.
And the people who are against it.
They say it sets a bad precedent for developing these fragile mountain areas. They question if it even makes sense economically and say we should focus on energy efficiency and other renewables instead.
It's a classic dilemma, energy needs versus protecting the environment.
Yeah.
And the Trift project really highlights those big challenges we're facing globally. With climate change and limited resources, it shows how crucial it is to have careful planning, open and honest decision-making, and finding ways to make different interests work together.
Yeah, it's a real tough one. Makes you stop and think, how can we, keep progressing without wrecking the planet?
Exactly. And the Trift project, it shows something else that's super important: getting the public involved in these decisions. Spatial planning shouldn't be done in secret. It needs open discussion, a transparent process, right? It reminds us that these decisions affect everyone, and we all have a say in how to build a sustainable future.
Couldn't agree more.
Well, we've covered so much ground in this deep dive. Started with the Earth's core, went up into the atmosphere, then dove into economic geography. It's incredible how these things are all connected.
And the best part is, you're not just prepped for your exam, you actually have the knowledge to talk about the future of our planet, in a meaningful way. Analyze issues, help find solutions.
Exactly. It's not just memorizing facts, it's understanding the processes, how our world works.
And as you keep learning, keep exploring, I really encourage you to think big picture.
Yeah, how do these topics all tie together? How does climate change affect spatial planning? What are the trade-offs, between economic development and protecting the environment? And the big one, what can we as individuals actually do to make a difference?
Those are the tough questions we got to tackle moving forward.
This deep dive has been amazing. I feel like I understand so much more about how our planet works, the challenges and the opportunities.
It's been a pleasure exploring all of this with you. Remember, this is just the start. Keep asking questions, keep learning, and keep pushing for a better world, a more sustainable, equitable world.
Well said. Thanks for being here.
My pleasure.